Okay, so it's 12:02, so we will get started. Um, Hello everyone, and welcome to another QU Metsoc lecture as part of the CIM's Distinguished Speaker Series. My name is Emily Slosser, and I am a Logistics Director for the Queen's Metsoc Student Chapter. Today, I am pleased to introduce to you our guest speaker, Bernard Aubé. Bernard has 29 years of experience and specializes as an expert consultant on water management and treatment for mining and smelting operations worldwide. Bernard owns and operates Envirobay Inc., a mine water treatment consulting company. The company specializes in treatment of acid mine drainage, heavy metals, metalloids, and total dissolved solids, including sulfate. Today, Bernard will be discussing the importance of planning for mine water management and treatment. Without further ado, I will pass things over to you, Bernard.
Thank you very much, Emily. Well done. You make me look impressive more than I think I am. So this presentation was prepared as a keynote speech for a conference in Brazil recently. It wasn't prepared specifically for students, but I think that you'll find it all relevant and it's important for you because you guys are going to end up being the ones who are running the mines and being the environmental coordinators and such in the years to come. So I think it's something that hopefully will serve you in the future. So as Emily said, I've worked for 29 years. So the first 10 years of those, I worked at Noranda Technology Center. So Noranda is now part of Glencore. And that technology center was a great place to work to really learn everything there is to know because we had some good budgets. We were going all kinds of sites. And that's where I became truly specialized in water treatment, and which allowed me afterwards to become a consultant. Since those past 19 years, most of the time I had my own consulting company, but I also worked for a while at AMEC and did work all over the world, whether it's doing pilot plants, detailed design, building, starting up. That's my favorite part, is actually starting up a treatment plant, because you work for months at doing it and then you get to start up and get it running. It's like having a $10 million toy to really get going. And challenges are always fun, especially when you manage to get through it afterwards. So obviously I've done a lot of work in Canada. I've got a couple of plants operating in Chile, Peru, Dominican Republic, USA. Those were mostly optimization, but built new plants in Guatemala. Tanzania, what a great place to visit. That was an optimization, and have a high density sludge plant in Cuba. Now, my presentation is really not about the technical aspects. This is a philosophical and what you need to do. What is it about mining and why, really the importance, why you need to do the planning. So water itself in mining is everywhere. Whether you're doing heavy metals, copper, nickel, zinc, then you're doing flotation most often, gold, silver, cyanide leaching, heap leaching, sometimes with acid. Diamond mines use water. Iron mines use water, a lot of water actually in iron mining. So everywhere water is used. So, and most of these mines, especially in Canada, definitely all of the mines almost all have excess water and have to discharge water to the environment. There are some mines like in the Atacama Desert in Chile, where water is a precious resource. And there what you have to do is recycle. And all of this water that you have to be pumping it, you have to be storing it, you have to treat it, and it's got to meet objectives. And I'm going to talk about these objectives, and I'm going to talk about all of these things. But first, I want to do a bit of an aside. Now, I don't know what they teach you today in school, but the social license to operate is something that you've probably heard of. It's really about what the communities and what the population and the stakeholders view and how it affects government and policies. And that comes down to how your permitting gets done. So the social license to operate affects your permitting, but it also affects what happens throughout the world. So if you have any negative impacts, let's say a large company like Glencore or Vale, if they have at one site a significant negative impact, the Greenpeace and other non-governmental organizations will, take a hold of this, and it will affect this social license in other areas, and could even affect permitting for new mines for this company, but not just this company. It also affects other companies, because there's a whole view of mining. Mining are still seen as the bad boys of environment. And this is because for years it was true. But for the last 20, I would say even 40 years, most mining companies try to do their best and minimize the footprint that they affect. But to keep the social license to operate, the owner has to make sure that he doesn't take too much water and affect other water takers in the area. You have to have no spills and non-compliance events, and not cause any environmental impact or toxicity. You can also affect, without having any toxicity, you can affect public drinking water, because often you can have some hardness or high sulfate concentrations that come from your site that'll affect drinking water downstream. So I was talking about where is the water. Now you see the potable and sewage water here. I don't really talk about that. They're critical for a mining operation, but they're small volumes. And when you're doing the mine water planning for the mine management of the whole site, they're not significant. What is significant is the precipitation. So you got to understand, every drop of water that falls onto a mine site, that mine owner now owns it and is responsible for it, and has to make sure that if it comes off the site, that it meets discharge quality. So that is considered contact water. You also have mine groundwater. So whether it's an open pit mine or an underground mine, you have to pull water out, and that water can require some significant work as well. And I'll get into that. Seepage from your tailings dam, from your waste rock, and freshwater supply. The freshwater is often used for reagents, and gland water is for pumps. So for sealing the pumps, that has to be clean water. There's a lot of interaction between these different ones, but the process use, this is the big water taker. This is in the mill. When you're crushing, you use a lot of water there, and it's also used then in flotation or leaching. Storage, often the tailings pond, or you have specific storage spaces. Recycle water, which is most normally of your water process use. So that goes here, and the discharge that you put out. Now, mine water planning is about the quantity and the quality of each of these. You need to know how much you're going to have and what that water is going to look like, or what the water needs to look like. So planning is determining all of these and defining how it's managed. I'm going to talk about water quality objectives and then water management objectives. So the quality, when you're dealing with recycled water, it's really about the process efficiency more than anything else. Flotation is a perfect example for when you're dealing with heavy metals. You need to make sure that the water is not going to affect your flotation efficiency, because then it affects your recovery and it affects the amount of money that you make. And that's what owners really care about more than anything else. While some care about environment just as much. Scaling issues. If your water has high calcium and sulfate, you can have scaling issues. Toxicity, if you have thiosalts in your water that you're recycling and it's maintained stagnant in a pipe, I've seen this present some H2S that can be very dangerous. Environmental discharge quality, this is mostly determined by regulators. Also, in some locations, there's some community pressure to be even more stringent than what the regulators will have. And there's also some owners that want to meet half of what the regulated is. regulated parameters. So these limits continue to become more stringent, and there's additional parameters. There's two very strong examples of this year. The MMER, the Metal Mining Effluent Regulations, which also include diamond mines now. So there's a D in there somewhere. The additional parameters they've added this year, some ammonia limits, and also the arsenic limits have gone down from 0.5 milligrams per liter to 0.3 milligrams per liter. This is only in Canada, but all over the world, there's additional parameters and limits becoming more stringent. Part of this is because we can. So you'd think there's new treatment systems, there's better ways of doing it so that mine water management would become simpler. But it hasn't become simpler, it's become more complex. And a part of this is because these technical advances exist, stakeholders insist that you do it. Also, there's models that exist now, but they're harder to use than what we used to use. So on the water management side, well, you want to ensure, I'm going to talk later about the ponds and the water treatment plant flow rate, but to minimize the amount of water that you have to deal with, you want to divert all of your water that you can. So this is all about keeping clean water clean and it not becoming contact water. But you also have to make sure that everything that is contact water, that is contaminated, that you do collect. And so you want to minimize the footprint. And so if you can make your waste storage smaller, then you minimize contact waters that way. Another thing is progressive reclamation. Obviously, if you have an open pit mine and you have a waste rock pile that you're no longer dealing with, if you can cover that waste rock pile, then that water can be discharged directly without treatment. That's called progressive reclamation. Here's the example that I wanted to give about the diversion. So assuming you have a tailings on a bit of a slope, this is exaggerated, and the red here is the tailings pond and you have a dam, you always have some seepage, either underground and or through the dam. So we have seepage collection. This is the top view, the plan view. You have the seepage collection in the tailings. So this is water that you have to collect and treat. But you put a ditch and berm upstream of it and make sure the clean water is diverted. Now, this is showing a tailings, but it could be a waste rock pile, it could be an open pit, could be a mill site. You always try to divert whatever water that you can to minimize your footprint. So that's one of two technical slides that you're going to see today, not much. So you're going to hear a lot about quantity and quality because that's what it's all about. And the objectives are the easiest part. This one are basically handed down by regulators most times or determined by your metallurgy. But for the quantity and quality of your raw water, you have challenges at every stage. So the mining projects, this is before the mine is built and the owner is trying to make money, get the mine built. And then it goes to the new mine, operating mines, and mine closure. What I'm going to do is I'm going to give you examples of each of these. So for the mining projects, I'm going to explain, what the typical focus really is. And I'm going to give one concrete example. For new mines, I'm going to talk about the consequence of insufficient planning because the planning stage for new mines is done during the project stage. I'm going to talk about the right way to design a plant. This is the true engineering that you need to do for water management and treatment. And give you one typical new mine example. For operating mines, I'm going to go straight from that new mine example to 3 examples of operating mines and the consequences of not having done the right planning. And then how you avoid these water issues. And 2 examples for mine closure. So it should give you a pretty good overview of what it means. This picture is from a treatment plant in Wawa, that I built a couple of years ago, high density sludge plant. So it has nothing to do with a mining project. This was a closed mine. A lot of the pictures are just there because they're pretty. Some of them have to do with the slide, and I'll let you know when that's the case. So when an ore body is discovered, the owner, he just wants to turn this into a mine. How does he turn this into a mine? He's got to evaluate the ore body that he's got, see how much potential money he can make out of it, and then see what it's going to cost to make it and obtain the funding to develop the mine. So to do this, you delineate the ore with a lot of drilling. You prove the metallurgy by taking some of these cores, doing the flotation or the leaching that you need in a pilot plant, and prove that you can set it up. You plan your mine workings, decide if it's an open pit mine or if it's going to be an underground mine or both. You plan your waste rock and your tailing storage. And then if it's a far mine, you need access roads and power infrastructure. It can be very expensive. So these are all the main things. And often at this point, the owner is going to say for water, well, we'll just put 5 million aside for a treatment plant. It's not that simple. And by the time I'm done, you're going to understand why. So here's the first example at the project stage. All of these examples are real. All of these examples are projects that I've worked on. In this case, mining engineers designed the open pit mine and the placement of the waste rock. They were very competent engineers and they did the best job that they could. And then late in the feasibility stage, this is the point at which the owner is trying to get money to open the mine. He's almost done and he's just looking to convince people to fund the mine. And then a water expert gets involved. Water expert looks at it and he sees that there are 3 different watersheds where the waste rock is supposed to be set up. It's not a great plan. And what this means, and it's not entirely the mining engineer's fault. It's, the ore body was there where the watershed split. 2 of them went to one river and the third to a different river, if I remember correctly. And one of them was too close to a river, so you didn't really have any space to build a pond. This was an iron mine. And the iron, one of the biggest problems is total suspended solids. So you need to collect all the water that runs off, and you need to settle and separate those suspended solids. So at this stage, when this was realized, water management forced a relocation of these waste rocks. So all the work that these mining engineers did had to be redone. They had put some little ponds, but they weren't enough. And they were in high risk areas. So they had to force the relocation and the redesign of these ponds. So this caused some important delays right at the time when the owner is trying to get the funding. And the $5 million budget that was put aside for water was not enough. So what happens when you build a new mine and all of a sudden you've been operating now for a year and a half, and you have your tailings pond is just full, or a separate pond, because sites often have a tailings pond or they have a separate pond, especially if you do paste tailings, for example. You don't have a tailings pond, you need a separate pond. So your water inventory is full and it doesn't meet discharge objectives. You can't just discharge it. So you don't have time to do all the studies that you should do, as I'm going to explain later. And you don't have time to find the best water experts to help you. So what do? You build a panic plan. Now, what is a panic plan? A panic plan, well, often in these first couple of years, when the concentrator is just ramping up, you still have your process engineers and your metallurgical engineers who, they understand pumps, they understand tanks, and they can design this thing. So they read about, how you treat the problem contaminant, and then they design a treatment system. I'm going to talk about this a bit more. This is an example of using just material and equipment that's available on the site. you know, it's going to be expensive to move this stuff around, and the efficiency of the reagents and such is going to be low. This plant, this is raglan. It was published, and at raglan, getting lime is very expensive because you have to put it on a boat and bring it over. It comes in bags. It's not like a truck that's just dumping quicklime to your silo. And so when your system is inefficient, it ends up being extremely expensive. So using the material that you have on site is, you know, you can do that for a temporary urgent fix, but it's going to be an expensive temporary fix. The other thing is, when you're doing a pilot plant, a panic plant, you don't have time for permitting. So often the owner is just going to promise anything, but that ends up biting you in the future when you have to build some very expensive system. Now I'm going to talk about suppliers, because a panic plant, often you just go see a supplier that you know, I don't know, Veolia, Suez, Biotech, call them up and say, I need something. Now, there are some very good suppliers. This is a Suez Densideg here in the background, which I've used as a number of plants, and it's a very good machine. But some suppliers are not as reliable and will just promise anything to sell their equipment. The problem is the mine owner doesn't know. But the mine owner will often say, well, there's a guarantee on this, so for sure it's going to work. And if it doesn't, they have to make it work. Well, guarantees can always be disputed, and I've seen it often. And your design criteria is extremely important. Your design criteria says, when you go see an owner and you've got a guarantee, you say the concentrations are going to go as high as this, as low as that, and your flows are going to be maxed out as this, but can be as low as that. Your pH, your redox, you got to say everything, because the supplier, if ever anything doesn't work, he'll just say, well, you said these were going to be the concentrations, and that's just slightly over, so our system couldn't do it because of that. The other thing is that suppliers, well, they don't have a choice. They can't sell what somebody else makes. They sell what they provide. And that's not always exactly what you need. It might work, but your costs are going to be higher. And so custom solutions, basically, you look at what you have, you get a good water expert, you figure out what you need, and then you have a solution that's really designed for your needs. But that also includes suppliers. I mean, suppliers have made the clarifiers, they will make pump skids, reagent systems, some very good reagent systems. You can just get a flock system or a lime system. You call these suppliers and they'll give it exactly what you need. Again, you need the proper design criteria, exactly what you're going to need, but these suppliers will be able to help you significantly. So what happens when you build one of these panic plants? Well, often your capital costs are very high. One of the reasons your capital costs are high is because when you order something urgent, let's say a clarifier will cost about $1 million, average size clarifier, for solid liquid separation in the water treatment system. If you order it urgent and you say, I need to have this clarifier in 4 months, because that is urgent for a clarifier, they'll say, yeah, sure, we can do that. We'll have to move you ahead of some other clients. It'll cost you 25% more. So instead of being 1 million, it's 1.25 million. And so your $20 million plan ends up costing you $25 million. That's a significant increase in capital costs. Your operating costs, because it wasn't properly designed, will be higher. Your sizing, the thing is, if you do it right away and you say, oh, we'll build it this size, often it won't meet your high flow events, or it won't meet your low flow events. It won't be able to operate at the lowest flow that you need to operate it at. Using the wrong reagents, a supplier will tell you, here, caustic works really well, it's easy to use. Caustic costs 40 times the amount that hydrated lime will cost, and hydrated lime costs about twice as much as quicklime. So depending on your But quicklime, you need a slaker and all. So depending on your consumption, it might be worth going to quicklime. And you need to take the time and have the right experts to figure this out. The types of agitators in water treatment can be very specific. Whether you're adding air or whether you're dealing with a viscous slurry. Your pumps, same thing, viscous slurry pumps, you need positive displacement pumps. If your plant is not well designed, you may have a low sludge density when you could have had a high sludge density. Your sludge can be unstable. And so your waste disposal costs can increase significantly, or you have to move the sludge afterwards. Worse than this, your plant may not even meet the needs and you have non-compliance, which means you can end up with a fish kill, you can end up with fines, bad press, environmental impacts, and there goes your social license to operate. So if you want to open a mine somewhere else, or if you want to expand your mine, it might become extremely difficult on top of the fines. The worst case of all, and we've seen this in British Columbia, we've seen it in Brazil recently, in Europe in the past, is you hold back the water because you can't discharge it and you end up busting a dam. And this does happen. So what causes this panic plant? What causes the owner to panic at the last second? Well, you have the contact water, unexpected acidic drainage. Contact water is a lot of water that comes all over your site. And if you have waste rock or tailings that will acidify, you're going to get some acid mine drainage. Or some prefer to call it acid rock drainage. And now this unexpected acidic drainage used to be common up until the 80s, let's say the early 90s. Since for the last 20 years, there's been regulations, at least in Canada, that says that you have to test your cores, your gangue minerals, make sure your tailings and your waste rock is not going to be acid forming. And if it is going to be acidic, you have to plan for it. So that doesn't happen as often anymore. Internationally, it does. But in most places, even internationally, often the company opening the mine, if it's a large company that's based in Europe or North America, they know to check for this before they open a mine. Neutral drainage with a contaminant still happens often. For example, nickel can be very soluble at a pH of 7 or 8. Selenium, molybdenum, and arsenic are completely soluble at those pH values. Sulfate can be caused, or suspended solids. Often these things are not seen from the beginning. The processed water, well, the processed water here, I'm basically talking about the water that is stored in your tailings pond. Now, just about any flotation for copper, nickel, zinc, lead, they're sulfides. The great majority of them are sulfides, although some oxides may exist. And when you're milling and you're floating, you're adding all kinds of oxygen to this. So you're causing some sulfate to be formed through the oxidation of your pyrrhotite, your pyrite, and even your minerals that you're trying to recover. So, and then you send this to your tailings and you send it back into the mill. So the sulfate continually increases. So most flotation, most heavy metal mines have sulfate that is controlled by gypsum and around 2000 ppm. Now in Canada, there is no limit for sulfate specifically right now. There's some pressures in BC and there's some pressures coming, but internationally there are many, Brazil, Peru, Chile, the whole European Union, and many places in Africa have limits for sulfate. Ammonia, well, ammonia is from blasting often, but that can be managed. But it's also from, in gold mines, when you use cyanide, the SO2 air process that destroys the cyanide creates ammonia as a byproduct. And also other reagent accumulation through the recycle, and also thiosalts generation. This still happens. It's often not thought of, but if you have any pyrrhotite in your ore, you can generate some thiosalts. And thiosalts themselves, they're not toxic and they're not regulated. But what happens is if you have the thiosalts, and you'll have to look it up because I don't have any chemistry on here, but if you have thiosalts, what happens is when you discharge into the environment, the thiosalts then oxidize. When they oxidize, they release sulfuric acid, bring the pH down. And there's been, I know examples of mines where the river was essentially dead because of thiosol generation over years, killing fish. And I have an example later of a fish killed due to this. Groundwater can also be a problem. Northern Quebec, there are some sites where there's high sodium chloride, basically saline water underground that can't be discharged due to high chloride content. So you need to treat that water, and it's good to know ahead of time. And to do that, you have to do your tests. And I'm going to explain exactly what you have to do. So the right way to do water treatment. You need to provide sufficient time to do the water treatment. You need to do the planning. You have to obtain the services of people who know what they're doing. You can't replace experience. You can't replace experience with literature. I've published over 25 papers, and most of these are on a specific project on which I worked. Now, these publications, you have 10 pages, and there's no way that in those 10 pages, I got to give the background of the plant, the site, I got to explain a little bit where it's located and what the problem is and what the solution was. But I'm not actually giving more than maybe 10 or 20% of what I learned on that site. So people who have been doing mine water treatment for years can help a lot more than somebody who's reading a lot of literature. So the right way to do water treatment, the key, the most critical aspect of water planning is the design criteria. You have to design your raw water quality extremes, your highest concentrations of nickel, let's say, zinc, and your lowest concentrations. Sometimes it's the lowest concentrations that can be hardest to treat. You have to establish the maximum quantity, that is a flood event. In Canada, we're talking 1 in 100 years. It's often a design recurrence that you have to use. If you have precipitation over 24 hours that exceeds the 1 in 100 year expected precipitation, that means you are often allowed to discharge some water untreated. You try to discharge the water that's the least contaminated, but you have to plan anything under the 1 in 100 year, you have to manage. You have to hold back and you have to treat and you have to discharge within regulations. Internationally, that doesn't really exist in most places, or often it's 1 in 20 years that is being used. Got a project right now in the Philippines. You can't even do a 1 in 100 days in the Philippines because they have so much rain. Sometimes it's 200 millimeters in one day has happened in the past year. You have to establish your treated water objectives. This is the easiest part. Often it's just given to you by the regulators. But one thing that people often don't realize, you can't just do it based on the water quality and the water quantity you've had for the past year or the past 5 years, or what you expect to get in the next year. You got to keep in mind that that treatment plant, you don't want to build a new one 10 years from now. You know, these plants often exist for 30 years. So you have to look at the expected conditions for the quality, the quantity of the next 20 years. So this is the second slide on the right way to do water treatment. So when the water actually exists, you do a lot of analysis and you figure out what your typical water is. And this is how you get your design criteria on your water quality. You do some laboratory tests. Your laboratory tests will tell you about how much sludge you can create, about what your reagent consumptions are going to be approximately. And then you do pilot testing in a continuous pilot plant with a sludge recycle. Now you really know what your concentrations are going to be at the end. So the water quality that you can meet for given different pHs, given different sludge recycles, how much sludge you're going to create and how much lime it's going to cost you and how much flocculant you're going to need. So you do all of these steps and your resulting treatment plant is using the right reagents. It's sized for your needs with the right retention time in the reactors, the right rise rate in your clarifiers. With experience, you have the right equipment for agitation, pumping, aeration in your treatment system. This is one thing that people don't realize how important the instrumentation is in a treatment plant and how important to have it at the right place. You can't have a tank where you're adding acid and lime right on the surface and have the pH probe sitting on the surface. It has to be at the outlet of the reactor, normally in a riser. This is very important because the way you control on a PID loop, proportional integral derivative, is based on what's coming out. And you can have excellent pH control if you're measuring it at the right location. Sludge density should be measured. Your turbidity is another great example. Often you have high scaling waters from a high density sludge plant, and the turbidity that's chosen is the cheapest one that you just hang in your clarifier. But you do that, it scales up, and 24 hours later, you're not getting a good reading. You can clean it every day, but it doesn't last. So there are surface scatter turbidity meters that get around this and can give you a good constant reading. So each of these steps above are critical for a good plant success. So how do you avoid the panic plant? Well, for new mines, it's really in the pre-feasibility and feasibility stage. It's in the project stage that you have to define your water quality and quantity. So your cores are not just for the mineralogy. Right? Geologists and juniors love to poke holes all over the place and get a whole bunch of cores. But you got to take the gangue minerals and you got to take what's below and above your ore body and see what the waste rock is going to be like. You have to do acid-base accounting and humidity cells and leach tests and lots of samples. Now, this is regulated in Canada. You have to do these steps. But in many places internationally, it's not regulated. You still have to do these steps. So in your mineralogical studies, I talked a bit about how you take your ore from your cores, you grind it, and you do flotation tests, for example. And often the water people are brought in after this is already all done. But what you should be doing when you're doing your flotation tests is simulating tailings, maybe a bucket, and then recycling that water. And this will tell you if you're accumulating a lot of sulfate, if you've got something that's dissolving in your ore and you're creating salinity, or if you have thiosalts. It also better represents your flotation because in the real world, you do recycle this water. So it'll give you a better result for your mineralogical study. Other things about poking holes all over the place is these boreholes, water is used to do the drilling. But once you're done with that, you purge that water out and see what the groundwater looks like to see if there's any salinity. Again, this is not a panic plant. This is a mine in the Andes in Chile. This is a large clarifier and just a pretty picture. So hydrology, you have to figure out what your 1 in 100 year recurrence event looks like. Hydrogeology, worked for a mine in Peru where they hit a big fault and they had like 400 cubic meters per hour coming out of water, and water that can't be discharged directly because the sulfate concentration was too high. So you want to keep clean water clean. That's all part of diversion and progressive reclamation. When you don't have water, you can do some benchmarking. So you look at similar ore bodies to what you're dealing with. These mines often have thiosalts. Sulfide flotation, you always have high sulfate. Gold mines have high cyanide and ammonia. You have to plan for that. Iron mines and gold and diamond mines often have high suspended solids. And these are just some examples. So you do your detailed water and mass balance. This says it's the third slide for new mines, but this is for all mines. So once you have your estimates for the quality, for water at different locations and for the quantity, you do the mass balance and you have your design basis for any treatment that you're going to need. Because now you have concentrations at each specific area. You got to ensure capacity to hold back water for the start of the mine life if you can. So what I'm talking about here, so when you have a mine that's going to operate for, let's say, 20 years, and you don't make your initial dam as high as you're going to need for the whole 20 years. You often make it for the first 3 years, and then you start putting your tailings in it. But if you do it instead for the first 5 years, then you have more space, and maybe you can use that tailings pond to hold back some water. And this gives you time to understand what your challenges are going to be, what your concentrations are going to be, and you can build the right plant. So treatment systems, the costs are based primarily on the flow rate. It's really not so much what you have to treat as it is the flow rate, except for some very specialized areas. That's what matters most. And water management is a combination of flows and ponds. Now, this is my second technical slide. So on the y-axis, you have the costs here. Here you have the plant flow rate. So flow rate from low to high. So for example, if you build a very small plant that will take care of your average water for the year, then you have to be able to hold back that water in your spring freshet or your wet season. That means you have to have a very large pond. So the pond and plant together are very expensive. Now, let's say you build a very big plant that can take your freshet directly. Well, then you need a very small pond. But your plant is going to be so expensive that the total is also very expensive. So at most mine sites, you do estimates of what your plant is going to cost for different flow rates. You do estimates of what your pond is going to cost for different sizes. And then you put your optimum plant size. This is something that should be done whenever it's possible. Now, back to examples. I have 4 straight examples here. So this is a new mine in the tundra, where as per the local regulations, they use the cores for acid-base accounting and basic humidity cell tests. And these showed that there was no problem. So the EPCM contractor, the engineering company that was building the mine, they said, well, there's no problem with the contact water. So they just built a big pond and basically put the waste rock right on the edge of the pond. No way to control the water that's going from the waste rock to the pond. The pond's right at the toe of the waste rock. After 2 years of collecting water, they find that the water, well, it's true, it's not acid, but nickel concentrations are about 10 ppm when the limit is 0.5 ppm. So what they do, well, they separate part of the pond. So they had to build a new dam, and then they bring in some lime, throw lime at it as much as they can, bring the pH up real high to get the nickel down. And then they have to let it settle. And then before they discharge it, they have to add acid. So this was extremely expensive. And this was a temporary solution that lasted a few years. And then they put a permanent solution, which was also a lot more expensive than what could have been done otherwise. At the same site, they had thiosalts. And they had no idea that thiosalts were going to occur here. It came as a big surprise, especially that they were doing paste tailings disposal. The only reason they noticed this is because they failed toxicity tests at the effluent. So they had a non-compliance, which if you're a mine operator, you want to have 0 non-compliance. So then they had to build some new ponds for greater retention time or increase the size of some ponds. and add some peroxide to oxidize the thiosalts before discharge. Here's a good operating mine example. This is one that I'm actually working on right now, where it was an open pit mine. It is an open pit mine that had a treatment plant that was working really well. So they were always in compliance. And then a couple of years ago, they put in a permit for expansion and they got it. But nobody took into account that the larger footprint causes more contact water. So you have a lot more water to deal with. And when I say a high runoff event occurred, I'm talking about a regular spring thaw. Nothing, we're not talking a 1 in 100 here. We're just talking about the spring thaw happens and they find that the pond system is too small, which means that they didn't have enough space for the solids to settle. The reagent systems were under capacity and the pumps, they had to add some diesel pumps, which are still there, to be able to transfer the water. So this is very expensive. Well, first there was a non-compliance, but then it becomes very expensive to be able to keep up. Another operating mine, this is actually quite common for gold mines because gold mines use cyanide, and then as they destroy the cyanide, they create ammonia. And so their high retention time, often the ammonia doesn't evolve at all during the winter under ice cover. And in the early spring, you get a lot of water, but the ammonia is still high. So you got to hold back that water and you got to give time for the ammonia to naturally degrade, evolve into the atmosphere. But what happens is you have a gold mine and you have a tailings capacity, and as you fill the tailings pond with tailings themselves, there's less space for the water. So the water retention time is decreased and insufficient. So you can end up with toxicity at the effluent because of ammonia and a non-compliance. Final operating mine example. So there's a mine in Europe that had an extended life. They found new ore and moved their cutoff so they were able to get to extend the life of the mine. The tailings capacity, well, it's in an area where there's not a lot of space. So they decided to go to paste tailings disposal. Well, by going to paste tailings disposal, this removes the tailings pond. And they didn't even realize they had thiosalts. Thiosalts were oxidizing in this tailings pond. So they were treating the water and discharging all within compliance, but then resulted in a fish kill because the thiosalts oxidized in the receiver. So a big study, a new treatment system, and a new separate pond had to be built. Could they go back now? They probably wouldn't go to paste tailings or would plan things completely differently. So how do you avoid the panic plan for operating mines? Well, your water and mass balance that I talked about for a new mine, it's got to exist for an operating mine, and you got to look years ahead. If you have any expansions or any major treatment, any major changes, you got to include water management in this. You can do tailings dam lifts before they're needed for tailings, when they're needed for water. Again, this is particularly for gold mines. Another thing is you always have to keep an eye on regulations. I mentioned that the arsenic and ammonia regulations have changed here in Canada, and this is being promulgated in June. I expect that there's going to be a few mining companies that are going to be taken by surprise, where their arsenic concentrations have been below 0.5, but not always below 0.3 milligrams per liter. So they might have to do something about that. Or where ammonia, which wasn't regulated before, is now being regulated, sorry. Changing ore body can change your water quality, especially for things like thiosalts and metalloids. And if you change your process or your tailings deposition, you got to know this will have water impact. So it has to be part of your planning. I have two mine closure examples. So a copper zinc mine, this is the GECO mine that operated in Ontario, Northern Ontario, for 40 years. In 1995, they were closing down. This has all been published. And they decided, as they were closing down in their last year, a really smart, really good idea to build a new lime plant while they're still making money, to use the money they're making to build a plant in the last year of operation. What they didn't realize, though, is that in the tailings, they were sending water that had a pH around 9.510 for copper zinc flotation. And then they were sending this water back. So there was a lot of recirculating water that was keeping the tailings relatively alkaline. And then when this alkaline water recycle disappeared, well, the tailings essentially blew up. So for years, they were having, sulfate concentrations that maxed out around 2000 ppm. Then they closed down in 1995. Within a year, they were up above 4000 ppm. So the new plant that they built could not meet discharge because the solids loading to the clarifier were too high. So the TSS was too high coming out of the clarifier. So we put in a sand filter, which worked great for the first few months. But then when you have calcium and you have sulfate concentrations this high, you have gypsum precipitation, which holds the sand together and doesn't work well. So within 10 years, they had to build another new plant that would meet the needs. Here's an example. This has also been published. This is Metsoc in northern Quebec. So they had a large open pit that now holds about 30 million cubic meters of water. At the time, there was about 20 million cubic meters of water when they noticed that the zinc concentrations were about 10 milligrams per liter, while it was expected to be clean. The reason it wasn't clean is because the concentrator site is around here, and there had been some contamination of some peat, some local peat with acid mine drainage. So they had to remove, for closure, they had to remove this peat, and they decided to put it in the pit, which was the easiest place to put it. But they didn't realize that while flooding, all of this zinc was released from the peat. So if they had put the peat somewhere else, they could have saved a huge study and do a batch treatment. The batch treatment, this is the lime injection that we were putting in. It took a couple of months, was a great success, but cost a lot of money that could have been avoided. So a summary of the mining examples that I gave you. For a project, there was a significant feasibility delay because the water people were brought in late. You had unexpected neutral drainage at a site because they weren't real water people who were evaluating what's going on with the waste rock, and didn't realize that nickel was going to be discharged. Also, thiosalts were formed. A nickel mine, that's common. For operating mines, if you're going to expand, if your tailings pond is filling up, or if you're going to paste tailings, you always have to take that into consideration for your water management. And for mine closure, you got to take into consideration that significant things are going to change when you're not putting alkaline tailings, and also the waste disposal in the pit. So this should be modeled, and you know what's going to happen beforehand. So who's responsible for this? Well, essentially, you guys in a few years, when you're going to be either an owner, a mine manager, an environmental manager, the owner is always responsible. And in the project stage, he's the one who's got to make sure, he or she, the mine owner, has to make sure that you're not only focused on the potential revenue, because it's really all about delineating the ore and making sure you show there's a lot of money and you can do the metallurgy. But you got to look at the water early on. It doesn't cost a lot to look early on. It can cost a lot if you don't do it later on. Mine manager is responsible for everything that happens on his site. The environmental manager, it's actually his job. But the problem is most environmental managers are so busy putting out fires and taking care of the day-to-day that they don't have time to do this. Regulators are also partly responsible, because they got to make sure before they give a permit that the owner did all the work that needed to be done, and they should not allow a mine expansion without expanding the water system. So in conclusion, planning for mine water, it's critical. It's critical to avoid a panic plant, which is very expensive and inefficient. It's also critical to maintain, for the owner to maintain a social license to operate. So it requires only really three things: your raw water quality, your water quantity, and your quality objectives. But this is the difficult part, is you must do it for the future. Thank you very much. If anybody has any questions, or Emily, you want to take over?
Yes, thank you, Bernard, for that awesome lecture. I definitely learned a lot. And yeah, we can get into questions. I actually had a question of my own. I was wondering, would you say it's more common than not for a company to find themselves in a panic plant situation? Or how often would that happen?
Well, it's less and less common because we're learning from our mistakes as an industry as a whole. So the initial plant often doesn't happen because we're being forced by regulations, among other things, to do the homework that needs to be done and see what the water quality is going to be like in the future. It actually happens more often, I would say, in operating mines nowadays. And like I said, for expansion, and how do you give a number for the percentage that it happens to? It's very difficult because you have different operating plants that may have something early on or later on in their life, or not at all when they do their homework.
Awesome, thank you. Any other questions?
I have a question. When it comes to mines, they're usually located in very remote areas. Sometimes can be even like, I guess, like red deserts or just more dry conditions. So what if there's a location that doesn't really have access to just water? Like, what happens?
That's a great question. So I've worked on a couple of projects in the Atacama Desert, which is the driest desert on Earth. So that can really serve to answer your question. There's two places where water can come from. Part of it is imported from Argentina over the Andes. And in other cases, the water is actually seawater that is cleaned, or the salinity is removed by reverse osmosis and then pumped all the way up to the mine, because the Atacama Desert is actually at a fairly high elevation. And so the pumping is significant. And at these sites, recycling water is critical. So you have a lot of the same issues. It's just that your objectives are really around recycling water and not discharge quality objectives.
Okay. Thanks so much.
Well, my pleasure. Doesn't seem to be any more questions. And the hour is done, so I think that the timing is good.
There is actually a question in the chat if you had a couple minutes. Aisha wants to know,
are there ways in which material science degree in the mining water, are there any ways in which a material science degree is applicable?
Is useful. Yeah, or applicable.
Yes. I hope so. I haven't studied that. I'm a chemical engineer by training. I went to University of Waterloo, and I had a work term. My first work term for a mining company was really because they paid more than others. But I ended up going into environment, and in fact, did one of my reports on ammonia, and then went to Noranda Technology Center. So really, it's more about the experience, because in that experience, I became fascinated with the water and with protecting the environment. If you're interested in that, I mean, you connect with some people who do it, and try and find some jobs in that area. I myself have been doing it 29 years, and I find that I get something back because, I'm saving fish. I'm doing something that is useful, that is productive for humankind and for the earth. So it's nice to be able to work in that kind of a domain. Now, as far as your material science degree, I guess that's similar to chemical engineering. And you know what? It doesn't really matter so much what you study. It's really how you use it afterwards. Because in university, you learn to learn. And once you've got that down pat, get to work and use it.
That makes sense. Thank you. I had one last question, actually, if you had the time.
I do.
I was just curious, since we're talking about planning, how big of an impact, if any, things like seasons, winter to summer changes, how things like that affect the water treatment plant setup. Like, are there moments where there has to be changes made, so like sort of a panic mode, or is it always just accounted for at the beginning when constructing the plant?
Okay, that's an excellent question. I'm going to give you a couple of examples if you have the time to listen. This plant here, this is in Wawa. It's a new high density sludge plant that I built I did the process engineering for this plant and was started up 3 years ago. It'll be 4 years this summer.
Right.
This one is treating water that comes from an old shaft. So it's basically contaminated groundwater. And what we did is we designed this plant to operate only in the summer. In the winter, you can only access it with a skidoo. And the reason is it's easier to operate in the summer. You don't have to have heating. You don't have to deal with all kinds of freezing aspects. So when you're dealing with a closed mine site, or if you have a large water body like a closed open pit, often in Canada, this is what you do. You design it to operate just during the summer months. So the capacity is twice as much as what you need because you're only operating 6 months a year.
Right.
Now, in an operating mine site, or if you don't have a lot of capacity to hold back water, then you have to treat in winter. And yes, the water qualities are usually, you have a freeze out effect. So if you have some raw water being stored somewhere and you're losing 1 meter of ice, basically what freezes is the ice. It's not the metals. So what's underneath it becomes more concentrated. And you don't have the precipitation dilution water. So when you're planning your treatment plant, this is part of what we're talking about. In the winter, you have lower flow rates to deal with, but higher concentrations. In the spring, you have very high flow rates, but lower concentrations. So your plant has to be able to take care of all of these different parameters. And so your design criteria has these extremes. Does that answer your question?
That makes sense. Thank you.
All right. Thanks so much, Bernard. Queen's University is very thankful for this presentation. And for everyone, you can be dismissed. Thanks for coming. And I guess if there's any questions on how to contact Bernard, I assume he would be open towards the contacts, and Nufu can, or any of our outreach directors would be available.
There's my website, envirobay.com.
Perfect.
Thank you.